Yeah, hello everyone. Indeed, it's a pleasure to be here in real life, but I guess that's clear to everyone. So today I'm going to talk about foundations of gravitational waves in cosmology, because I think this is a topic that still has many unexplored questions. So I hope to excite you about it. So as in pretty much all of physics, an invaluable tool that we have is perturbation theory. So ideally, right, we also in GR, right, we like to say something like, oh, okay, our problem is difficult. Let's, split our metric in some kind of background metric, say flat space or the curved spacetime, maybe FLRW, plus some perturbations. And this works wonderfully for many settings. But of course, right, there is no canonical split, right? If I give you some kind of, physical metric, right, say, even, from a numerical simulation, right, two black holes going around each other or something, there is no split that tells you, okay, this is your background and that's your perturbation. And that's, of course, something that we like to do, right? Because we typically like to think of the perturbation as our, gravitational wave and the background as, the background, the static part. But there is no such thing as a canonical split. Luckily, for us as theorists, there's a way to sort of run away from this all. Right? So what we do is, right, we have our messy physics, complicated, whatever, matter flowing around, strong gravity, all of that, I'll hand over to my numerical colleagues or something like that. And then I run as far as I can very quickly, all the way to infinity, where things become much nicer. And I, as a theorist, can do my experiments and rigorously study gravitational waves. So how does it work? Well, you have to run in the right directions to study gravitational waves. Right? As you know, there are different infinities in general relativity. We can keep time or space fixed and let time run to infinity. Then we end up at time like infinity. We can keep time fixed and run all the way sort of to r equal to infinity. We end up at spatial infinity. But of course, radiation, right, as we know, sort of propagates along null geodesics. So to study radiation, we have to run along null directions. Of course, none of us can actually do that, but theoretically we can, of course. So the radiation zone is there. Now, of course, infinity doesn't quite fit on this page because, well, it's infinitely far, but there's a trick that we can use. And the key idea is essentially to bring infinity to a finite distance. And that goes by the name of a conformal completion. Right? So if I have my, my beautiful manifold here with some metric on it, say even just flat space, right? Then the points at r equal infinity are not included, right? Because that's, well, all the way at infinity, and that's not where my metric is well defined. But what we can then do is do a conformal completion. So we can rescale our metric with some omega, and then attach the boundary to this spacetime. So if you want, what you do is this omega, typically you can think of as being 1 over r. So that, r equals infinity is equal to omega equals 0. And now if you rescale everything, this metric is nice and smooth, also at omega equal to infinity, and we can attach all those points. And that's, that trick is essentially behind this picture, right? Or I hope all of you have seen this conformal diagram of flat space-time. You use this trick of a conformal completion to draw this, right? Because now, all the infinities nicely fit on this screen, right? So we have time like infinity, space like infinity, and this is our radiation zone called SCRI as well. So that's where I'm going to study gravitational radiation. Now, of course, flat spacetime is very boring, right? Or, I mean, it has many interesting properties too, but of course, ideally, we like to study more complicated systems. Say, for instance, a star that's maybe static for a while, wiggles, emits radiation, and becomes static again, or, whatever, your binary black holes merging, all of that we like to study. So we like to define a large class of spacetimes that we can then study all sort of at the same time. And we do this with this this definition of an asymptotically flat spacetime. So the construction is very similar, right? We say, okay, whatever, we have some physical spacetime. The points at infinity are not included, but we're going to use that trick of having a conformal completion. So we're saying, okay, we're having some omega and a new metric, right? This GAB that is smooth everywhere at the boundary, which I denote by this hat. This omega is 0 and its gradient is nowhere vanishing. That last condition ensures essentially that omega is a good coordinate that I can probe away from scry. So, and of course, a technical condition is that we also demand that the topology of this surface is R cross S2, just as you kind of would expect if you think of the canonical examples like a curved spacetime or flat spacetime, etc. Now, up until this point, up until point 1, essentially, I didn't do any physics, right? I just did geometry, no physics there. But of course, right, I like to study gravitational waves. So I'm going to impose Einstein's equations. And I'm interested, right, in this idea of being asymptotically flat, right? So, you know, I need to move far away from a system and there shouldn't be too much matter and other stuff flowing around because that would curve spacetime. So I want my stress energy tensor to decay at a particular rate. So, you know, that translates to this technical condition that omega to the power -2 times the stress energy tensor needs to have a smooth limit. Okay, so that's our definition. That sounds maybe rather technical, but what does it do for us? Well, actually, quite a bit. Right? So already at this stage, if I look at Einstein's equations, what pops out is that that surface, that scry, is a null surface. Right? So the picture that I drew before was correct, right? So it's not something that we put into the definition. It's a result from, you know, just those very mild conditions that I demanded. Then, of course, right, associated to that, well, since this is a null surface, then as you can imagine, the induced metric on this surface has to be degenerate. So it has signatures, well, 0 plus plus. And these two, the normal to this surface and the induced metric are, you know, sort of the stars of the story. They're going to form something that we call the universal structure and play a key role. Now, you may object at this point and be like, well, that omega that you chose seems like you can choose, well, pretty much anything. Not anything, of course, but, you know, if I have some omega that, you know, satisfies nicely this definition, is 0 in scry, etc., then, you know, if you would like to take, say, 10 times my omega, that works too, right? That's also a perfectly valid choice for your omega, or essentially any, you know, smooth function that isn't, you know, 0 somewhere else is a good choice. So that seems not so convenient, right? We have all this freedom. That just is, and that, you know, this omega is something that you introduced, right? As it's like a mathematical tool. There should be no physics in it. So in the end, right, whatever equations you derive should be invariant, conformally invariant under this choice. So just so you're aware, right, we have this omega, we can make a different choice, call it little omega, then our metric will rescale, also our normal will rescale. You can see that this omega inverse comes from, you know, simply the definition of what the normal is, right? So since the metric, the metric goes, you know, with omega squared, so the inverse metric goes with omega to the power -2. And if I then, you know, expand this gradient, we see that this little omega cancels one of the inverse omegas here, and I end up with the omega inverse NA. So there's some conformal freedom. In the end, we don't want our physics to depend on it. As I said, right, our Q and N, right, they form the universal structure. So they're the same for any asymptotically flat spacetime. Right? So if I take, say, the curved spacetime, I can already tell you what, you know, if I introduce some coordinates to something, what this Q and N should look like, right? Because it has to be exactly the same as, say, Minkowski spacetime. If you choose some other, you know, asymptotically flat spacetime, you know, I can always introduce coordinates such that they're the same as in flat spacetime. And that's very useful, right? So this is a very rigid structure. Of course, different asymptotically flat spacetimes, you know, should also describe different physics, right? different physical spacetimes. So, and that all is hidden in the next order structure. So gravitational radiation, for instance, is not part of this universal structure, but is encoded in the next order structure. Now, this to me, I think is very beautiful, right? So the key point is nowhere in this story did I introduce some split of background plus perturbations. Right? All I did was run us away as far as I can. And at null infinity, this split naturally occurs, right? This universal structure is like a background. And that first order structure, or that next order structure, is where my gravitational radiation lives. And this is completely, fully nonlinear, right? I didn't need to assume any epsilon, being small or anything. This is properly nonlinear. So I think this is very, very beautiful. Yeah, you have a question.
I was about to cry too. But...
Yeah, to me also. When I learned.
No, I wanted to ask, dependent. There may be other symmetries of the asymptotic metric, right? Or
yeah. I'll come to the symmetry story. I will do that. Nice. Of course, right? If you thought, okay, that geometric definition that you gave sounds a bit complicated. I like to do GR and coordinates. Of course, you can do that too, right? The whole story that I told you about, we can introduce coordinates and just say, well, if you find a coordinate system in which your metric has this particular form, and it's a bit messy, I'll order it a bit, then it's an asymptotically flat spacetime. That's completely valid construction too. So how does it work, right? So of course, right, any metric you can write in this form on the top. And for it to be asymptotically flat, what we want is that it decays in a particular way. Right? So essentially, if you have this r coordinate, tells you how far away from this surface you are. So what we want is that at leading order, essentially, we have flat space, right? That is, in other words, sort of saying that our universal structure is the same for all asymptotically flat spacetimes. And then, we want to also describe different physics. So for instance, right, we may want a spacetime with a mass, like, say the Schwarzschild spacetime or the Kerr spacetime. That will be hiding in this coefficient up here. We want to describe radiation, that will be hiding down here, or say the angular momentum aspect, which will be up here. So you can, if you can find a coordinate system in which your metric coefficients have this particular decay, then your spacetime is also asymptotically flat. So these two definitions that I gave, are completely equivalent, and depending on what you want to calculate, one might be easier to work with than the other. Now, what can you do with this? Right? One of the questions was about symmetries. Well, you can actually study something that we call asymptotic symmetries. So generically, right, a given spacetime doesn't have any symmetries. Right? Of course, the analytic ones that we know have symmetries, but a generic spacetime, right, like that we see in all these numerical simulations, there are no symmetries whatsoever. So, but we like symmetries because symmetries can do a lot for us. So the nice thing about this formalism is also that as you go to infinity, sort of you get this notion of an asymptotic symmetry. And there are two ways to say it. In the language of the universal structure, asymptotic symmetries are spacetime diffeomorphisms that leave that universal structure at scry invariant. And you can, say essentially, right, that the universal structure was given by a class of conformal metrics. So, these vector fields can only, conformally rescale my Q, and similarly for my N. If that sounds complicated to you, the coordinate equivalent statement of that is essentially, right, that you want something like a Killing vector field, but only at infinity, right? So if this were 0 everywhere, I have an exact Killing vector field, but now I demand that only at scry, at some particular order, this is 0. So that means that I now have an asymptotic symmetry vector field. Now, these asymptotic symmetry vector fields are not the Poincaré group, but the BMS group that you might have heard about. There's lots of research about it these days. although of course, the BMS group had been found, in the 60s and 70s already. And what it is, it's bigger than Poincare, because what we have here, it comprises of, our usual rotations. They live up here, but also something that we call super translations, right? So Poincare, you just have translations. And that would mean that, this F, has to be, can only be a constant or one of the first 3 YLMs. But in this framework, this F can be anything. It can be any arbitrary function on your 2-serum. So those are your super translations. And as a result, your asymptotic symmetry group is bigger. Now you may ask yourself the question, okay, well, whatever, who cares? What do I want to do with this asymptotic symmetry group? Well, my answer to that is it provides quantities, that we can calculate with a physical interpretation, right? So for instance, if I look at this BMS group, there is a nice translation subgroup in it, right? Essentially, right, when I just restrict this to the first YLMs, right, with L equals 0 or 1, then I get this translation subgroup. And that allows me to, to define something like mass or linear momentum. There's also, well, there's a subtlety there. There are many rotation subgroups, but anyhow, the rotation subgroups allow me to define angular momentum. And the super translations, they're a little bit trickier and a little bit less intuitive, but they're very closely connected to the memory effect. Now, of course, in all of this story, there was a critical assumption, right? The idea is that, as we move far away from our sources, our space-time becomes flat. And that bothers a lot of things, right? We get this nice BMS symmetry algebra, but also, and we have these Bondi-Sachs coordinates, we get peeling theorems, if you like, that kind of stuff. We have one of our R expansions that are very useful. We have some, tricks, projection operators, all the good stuff. But of course, right, expanding spacetimes are not asymptotically flat, right? By default, right, there's the spacetime, or at least, the canonical example, right, FLRW, the spacetime is homogeneous. So, doesn't matter how far away you go, your spacetime curvature never dies off. So Joe Weber asked the question then, to the people working on this framework, already in the 60s, so why do you guys actually assume asymptotic flatness? And Bergman replied, well, the only answer I can give is that people simply started with the mathematically simplest situation, or what they hoped to be the simplest situation. I think that's a fair answer. To which Bondi also added, some additional words and said, I regret it as much as you do that we haven't gotten to the point of doing the Friedman universe. And somehow, not much had changed since the 60s. So we decided to rectify that. So what, of course, physics hasn't done nothing, in the direction of gravitational waves in cosmology. Essentially, sort of the state of the art is typically within linear perturbation theory, which of course is extremely valuable, right? Just if we want to study the CMB, we're extremely lucky, right, that the anisotropies are so incredibly tiny that, in fact, it is a very valid idea to split our metric in FLW plus perturbations. Of course, these are the CMB are homogeneous solutions, right? So there's no source in our gravitational wave equation. If you want to study, gravitational waves from compact sources, right? Say, supermassive black holes merging very far away or something like that, we do need the inhomogeneous solutions. For those, what we typically do is sort of like assume everything is a flat space and then sort of change the mass to something like direct shifted mass and change the distance to a distance that accounts for the cosmological expansion, and we're all happy. Right? And that it relies on a geometric optics approximation. But, well, since, experiments are getting better and better and we're going to see sources further and further out, and just from, a theoretical perspective, I think this is particularly interesting, we decided to say, okay, what can we actually learn from the full nonlinear theory in this setting, in the cosmological setting, right? Because, do we still have something like the BMS group and all these other things? These theoretical questions are very interesting, and hopefully, maybe they also give us some insight about maybe possibly some nonlinear effects that we might see in our experiments. Now, there are two different cases that we should distinguish. The expanding spacetimes, there are sort of, well, I guess two classes that we can consider. Those that accelerate, so for which the expansion goes faster and faster, like our current universe and any universe with a positive cosmological constant. And those that decelerate, where the expansion, slows down, such as, for example, a matter-dominated or radiation-dominated era. The two are rather different. In particular, right, if I draw their conformal diagrams, then the decelerating spacetimes have this kind of diagram, whereas the accelerating ones have this kind of diagram. And as you can see, this radiation zone that I've marked here in blue is rather different for both. Right? So here, it is, again, a null surface, like an asymptotically flat case, but here it's a space-like surface. So it's very different. As a result, the two situations you cannot sort of handle mathematically in one go, and you have to treat them one by one. So this actually is a very interesting story as well, but I'm not going to focus on that one today. I'm going to restrict myself to this class of spacetimes, the decelerating ones. So,
Beatrice, may I abuse my position?
Sure.
But I thought that the conformal diagram for, let's say, a radiation-dominated universe, it's the same rectangular shape, right?
No, for a decelerating one, actually, well, I should say
Even
for FLRW, it's this diagram.
Right, but there is it's still rectangular one.
No, the rectangular one is for the sitter, say, but it's
also for radiation-dominated universe. And
no,
okay, I'm mistaken. Good. Well, we can discuss
I will show it to you in a bit.
Perfect. Good. Okay, please continue.
So, right, if we write down our decelerating FLW spacetime, right, we can write it in many different forms, but this one is, I think, particularly useful. Right, we have our conformal factor times flat spacetime. Then, the scale factor essentially scales with eta to some power s. Well, s to the power 1 minus s. I've introduced this s because it will turn out to be convenient for me, but s is essentially, you should remember, related to w, and w is our equation of state parameter. So if I want the spacetime to be decelerating, I need w to be between -1/3 and infinity. Just to give you a little bit more intuition, right? This is the equation of state parameter. So if w is 1, we are describing a stiff fluid. 1/3, we're describing radiation. 0 is dust, and -1, right, is not included, and that could, mimic a cosmological constant. Now, quintessence. Yeah, that's tricky. If if the quintessence is,
quintessence is still in the non-describable.
Is typically an accelerating regime. Yeah, that's true. So the philosophy that I'm taking here, I'm looking at sources that are far away, that have propagated mostly through a time that our universe wasn't accelerated yet, right? That's in a way fairly recent, so I'm kind of restricting myself to this class. But I agree, if you're looking at our current universe, it is an accelerating universe, or if it's a quintessent universe, it is accelerating.
Yes, my point about you already answered was that maybe you don't need to care about this if quintessence would be already in the right branch, but it's not it's in the de Sitter branch. Yeah.
Yes. Typically quintessence is right with a W, around -1. Yeah. Good. So I got a question about the conformal diagram. Well, to construct that conformal diagram, let me not, focus on the details too much, but what you typically do, right, is you do some coordinate transformations, and then you choose your right conformal factor in some coordinates. And if you do all that, right, what you end up with, don't need to follow exact details, but you end up with this very simple looking metric. And the nice thing about this metric, right, is that now, right, initially v equals to minus u and v equals to pi were not part of the spacetime because, well, essentially the scale factor diverges there. But now the metric is smooth at those positions. So I can include those boundaries. And then what you get is this spacetime. The details are, not new, right? You can actually open your GR book from Sean Carroll, and one of the appendices, he actually does this derivation. And as you can imagine, right, that this the space-time, the conformal diagram looks like this. Right? So here I have our Big Bang, and this, is our interesting regime where omega is 0. Or another, in the coordinates that I introduced, the u and v coordinates, this is where v equals to pi. So this looks good, right? But in fact, actually, if I look near Scry, what I find is that the omega that I've chosen actually is not so nice, right? Because it scales with, at Scry, v is equal to pi. So that means that, as long as s is different, well, s is between 0 and 1, right, in this case. But as long as s is different from 0, this is not smooth. Similarly, right, the gradient actually vanishes exactly on Scry, right? When v equals to pi, as long as s, right, is bigger than 0, this vanishes. Those were sort of two conditions, right, in our previous construction that we demanded, right? Omega had to be smooth and the gradient had to be non-zero. And then you may say, okay, well, no problem, right? Beatrice, you told us before, conformal freedom. We have that, right? So why don't you just, you just made a bad choice for omega. Why don't you choose a different omega where you somehow absorb all the badness, right? And you can do that, right? So if you take a little omega and rescale it, all that, I can create an omega that is smooth and whose gradient is nowhere vanishing on Scry. So you seem to be in business. But then you introduce another problem, because then your new metric, right, also changes. And in fact, now your metric actually diverges on Scry. And that's no good, right? Because the whole point of conformally rescaling is that, that you have a smooth metric at infinity so that you can use your usual tools of differential geometry and don't have to worry about any things blowing up. So it seems like you're a bit of a pickle here. So what to do? Well, there is actually a very simple resolution. We can note that omega to some power, to the power 1 minus s is smooth and has all the nice properties that we want. So all we have to do is, right, keep our same omega to rescale the metric, but just define a different normal. So instead of having just the gradient of omega, we redefine our normal to be this, with this omega to the power 1 minus s. So that now, I do have all the desired properties. And this 1 over 1 minus s is just introduced for convenience. Of course, there's one other thing that's drastically different between asymptotically flat spacetimes and these cosmological spacetimes, right, is the presence of matter, right? So for asymptotically flat spacetimes, we wanted the stress energy tensor to decay in an appropriate way, but FLRW spacetimes are homogeneous, so there's matter everywhere. So how do we deal with that? Well, in fact, if we actually study, right, FLRW exactly, we find that its trace is even non-vanishing. So it's not just decaying, but it's really not decaying. But it's actually worse than that. In fact, actually, it's diverging. So if you these normals are now smooth and nice objects. So if s is different from 0, this diverges. And I have another diverging term, and then the finite terms arise. So that's a sort of very different. Luckily, this sort of thing is universal. So this form is the same for any FLRW spacetime. Here, this is a little bit different, right? This tau depends on your choice of conformal factor, but even that is okay. So what we decided to do is, say, well, we have this nice canonical example of FLRW spacetimes. Let's define a large class of spacetimes modeled after these, right? Just as we modeled asymptotically flat spacetimes after flat spacetime, right? So essentially, we copy pasted the definition that we had before from the asymptotically flat spacetime, but we make these minor changes, right? We introduced this omega to the power minus s in the normal to account for the fact that we've seen that, you know, this makes NA a good coordinate and nowhere vanishing. And we said, okay, well, you know, the stress energy tensor is not decaying, but, you know, it should have these properties that its trace exists and that, you know, it has this particular fall-off. So, you know, this is that it can only have a diverging term that looks like this, and then all the other pieces should be finite. And then we said, okay, well, let's do the same thing as we did before, right? So let's study, for instance, what are the asymptotic symmetries? And again, right, that means that you study all the smooth vector fields that preserve your universal structure. And again, right, we have essentially a very similar universal structure. And what we then find is, again, something like the BMS algebra. So you can write that, right, as our group of Lorentz transformations and our super translations. But there's like a tiny little thing here. It's S dependent. So you may say, okay, well, Beatrice, I think, right, didn't we know that already? There was this paper from 2016 that also said, you know, BMS in cosmology exists. Done. But, you know, the story is actually a bit more subtle than what they claimed in this paper, because there's a technical point, right? That S, right, which characterizes our equation of state, right, characterizes that we have an FLRW spacetime, changes the conformal weight of this function in front of our super translations. Then you say, okay, well, that's very, very technical. What kind of, you know, I mean, who cares about that? But it actually has a drastic consequence, because the conformal weight is no longer 1, but 1 plus S. There is no longer a translation subalgebra. So, right, in our BMS algebra, we had these super translations, and then, you know, we could restrict to the first YLMs, and that, you know, formed a nice subalgebra. So we could define things like mass and linear momentum. But now there's no canonical way to do that. Now I have to deal with all the infinitely many super translations at the same time. There is no canonical translation subalgebra. So, yes.
Yeah, I don't get this point. So you said that there is no this. I mean, that there exists the separate translations. They exist, but they don't commute with the other part. Is that what you're saying, or they don't exist at all? Because you can always use them to say this is the equivalent of a super translation, and that will define my momentum. It won't commute with whatever, but that's my momentum.
So the thing about what I want to highlight is I have super translations, and there are many of them, and I can use them all. And I mean, that's fine. But sometimes we like to say, okay, well, but I want not just any super translation. I want a special one. I want the one that generates time translations. Mm-hmm. And the problem is to define that one, yeah, to define that single special one. Because, yeah, there is no canonical subgroup if you have something that doesn't have the right conformal weight. You can show, right, if you want a subgroup, you want it to, you know, close within itself, and it doesn't. There is no, you have to live with the infinitely many super translations all at the same time.
I know nothing about this, but naively, you could say, well, like I expand in S, and there will be a first order thingy that may be defining what I would call. I use, if you want, perturbation theory, but for what I would, I know you can do it, right? But,
yeah, no, okay. So if I now start to expand in S and things like that, you could do things again, yes, but that would sort of, in my opinion, that would defeat the whole purpose of using this powerful framework in a way, right? Because then you, in a way, go back to the linear case. And that wouldn't quite be the linear case, but you know, but just it would be deformation. Yeah, that's true. Yeah. So this is not quite right. So we've written a paper saying that there's BMS-like symmetries, not BMS exactly. And that, you know, as of now, or at least we don't have a solution to this, but that means that at the fundamental level, we don't really have, you know, for this larger class of spacetimes, right, we don't really have a notion of what mass and linear momentum is, right, because we don't have this translation subalgebra. Another thing is, right, so the next thing you want to do, right, symmetries are great because they provide that physical intuition for many things. Next thing you want to study is gravitational radiation. That, that next sort of structure is typically a bit more tricky. And, one of the challenges that for us, right, so we don't have quite an answer to that, how to study it yet within this framework. But one of the challenges also has to do with the fact that we don't have peeling. So, if we were to have peeling, essentially what you would want is that this is 0 and this is 0. And if you calculate it for this class of spacetimes, it isn't. Now, peeling, of course, is not holy in any way, right? You don't need peeling, but it is very convenient because it typically sort of rearranges and organizes everything sort of nicely in a hierarchical way. And yeah, we don't have access to that. So how many more minutes do I have? Oh, good. Okay. So you may ask yourself the question, okay, great, you provided me at least with one example, FLRW spacetimes, that falls within your class of spacetimes. Do you have any others? Well, I don't have any explicit ones, but what I can do is I can show, at least mathematically, that the class of spacetimes that we've defined is as large as the class of asymptotically flat spacetimes. So there are at least many, many spacetimes that fall within our class. Of course, that doesn't tell us anything about whether they're physically interesting, right? I may be sort of have found a way to define many sort of spacetimes that I know have things that we think are physically undesirable, that don't satisfy energy conditions, et cetera, et cetera. But that part the proof doesn't inform us about, unfortunately. Another thing that's still open and that you'd like to show is that, if I take FLRW and I perturb it a little bit, that falls within our class of spacetimes. Also, that we haven't been able to show yet, and still an open question. And as you can imagine, it's just a matter of computation to show this. Things are a lot more messy with all the extra matter flowing around. And your equations are more difficult to handle than in the case of asymptotically flat spacetimes. So just to conclude, I think that gravitational radiation, right, can be studied using asymptotics in the full nonlinear theory very beautifully using that framework. And I think sort of it's time for us, especially as experiments are progressing and everything, to also get our theory act together. And one of the ways for me to do that is to use this framework of asymptotics and study sort of these fundamental questions. So I mean, how can we define things like mass and angular momentum and all these other things for gravitational waves that propagate in our own universe, right, which is expanding. So what we found so far is that if you study the asymptotic symmetry algebra, right, which provides mathematical quantities with a physical interpretation, that it's not the same as an asymptotically flat case. It looks very much like the BMS algebra, but it's BMS-like, and in particular, right, we don't have that translation subalgebra. So I think there's still lots to explore. I also think that we should push probably the linear theory a bit more and see if we can get something beyond the geometric optics. At the same time, I think it's useful to have a multi-track sort of explorations because they typically reinforce each other. And I hope that I've inspired you to well, ask questions in this trend. Thank you for listening and your attention. I hope this is the right translation of thank you for your attention. I trusted Google on this, but sometimes you shouldn't.
Thanks to Beatrice for this very nice talk. By the way, you were probably, just to clarify, you were doing always FLRW spatially flat or open, am I right?
I'm restricting to spatially flat. Yes. Okay,
of course. No, yes. Then because in my mind I thought about closed universes, and then of course the boundaries are different.
Good. Yeah. Closed universe.
Yeah. So you were doing spatially flat.
Yes.
The other one, basically. Very good. Sorry about that. So, any questions to Beatrice? Diego, you continue.
Well, there is time, right?
Yes.
I guess again, not being from this field, I studied this long time ago, but what are the consequences of all this? So in the sense that, if I remember properly, all these Bondi mass, all these things was very important to prove that gravity waves exist, in a sense, that there is some kind of energy associated to them.
Yeah.
So do you imagine that your program eventually spits out that you cannot do the same kind of tricks for these backgrounds? Would you claim that it's not so clear that gravity waves exist, or what is the real physical?
What's the direct implication?
What is the physical?
Yeah, so I wouldn't dare to claim that gravitational waves don't exist, especially given
Einstein claimed it, so you can do it.
tested them.
Okay.
But indeed, it's not so obvious in this framework yet how to define things like indeed what the energy is of gravitational waves in these kind of spacetimes. I don't know how to define that in a rigorous way. And I think these questions, I mean, they seem maybe abstract now, but people didn't care about the BMS symmetries in algebra and super translations for the longest time. And now we see, that to get numerical simulations to be accurate, we need to account for this.
Yeah.
So there's lots of, recent work by the Caltech group where they have to be very careful about, memory effects and BMS super translations to even, make
for the nonlinear.
Yeah, because nonlinear effects are important, right? Yeah. And I mean, also, right, to even define, or extract the radiation from their numerical simulations, right? They're all relying on this framework by Bondi and others.
Sure.
So it's just the foundations. And of
but
course,
if I have a system, right? I have a system, a binary. I have my LIGO detector.
Yeah.
And then the gravity wave comes and does some work to my system. And for this kind of problem, I don't see how this can be, because it's a local thing. I have a volume. This is.
Yeah, you're saying so. Separation of skills. We should all be good, kind of. And I agree that locally, probably that. I mean, I'm just saying that the wave itself, once it hits the LIGO detector, right, that's all fine. But I'm just saying that it propagated over very, very long distances. And it's not obvious, right, that it didn't interact at all with the expansion of our universe.
I see. So
I
see. No, that's very interesting, of course.
And of course, right, I mean, it might very well be that these effects are whatever higher order, never relevant for
that's fine.
Observations. That could be true.
So I mean, the best outcome of this would be that through the propagation of the wave through cosmological times, it picks up, because of non-linearities, a kind of effect from the background.
Yeah.
That could be amazing.
And I mean, that would be the best. Yeah, I think, if we could actually see things like, it would provide maybe other ways of measuring the Hubble expansion, right? If there were more signals in the wave itself, other than just that, right?
Well, that would be amazing.
Things like that, yeah.
What about also this program of gravitational waves? Because, also the people doing more formal stuff like Strominger, these people there, I have no idea what they do, but I know that they are using the BMS they go to next order to next order, and they claim they understand very well that GR almost follows from that. No, they claim that GR kind of follows from this.
That's right. Yeah.
Could you say that? Hey, wait a minute.
Well, yeah, there are many. I think once you understand GR, I guess there are many ways to sort of say, well, GR is the most natural theory, and. But you are kind of saying that BMS is not so. The starting point is so okay, good. So
I ask you are saying that the starting point is the zeroth order BMS.
Yeah.
I think, right?
Yeah.
So I guess maybe we could have it we have this whole half an hour discussion.
Okay,
we can talk.
But we are gonna be in different rooms, maybe.
Well,
we can find each other afterwards.
Well, I can ask you this, but I think it's a relevant question, right? That there's a whole program based on BMS saying that when I do these gravity waves or next to next, GR kind of follows, and you are saying that the starting point may not be so robust in a
more general setting, right? Yeah. So, I mean, I think GR is much broader than just asymptotically flat spacetimes, right? Of course, I mean, if you have GR, there is a set of solutions that are asymptotically flat. We have other solutions that, right, are like this, that are, I would say, have a cosmological non-asymptote that are, FLRW-like. We have things that, have a space-like boundary at infinity. So we have very different classes of spacetimes. And, just to say, okay, I'm going to restrict myself first to this class of spacetimes. I know some properties of this. Now I'm bootstrapping myself to GR. It's to me not the most natural thing to do, right? To say, okay, first I have this set of solutions. Now I find all others too. But I mean, it's I guess more of a matter of taste than anything fundamentally being wrong. But yeah. But okay, it's just not my cup of tea. Let's put it that way.
So, guys, we have another question by Syed Takwi from Zoom. So,
hi, am I audible?
Yourself.
Hi, am I audible?
Yes, we can hear you.
Yeah, so I just wanted to ask a short question. You said that asymptotically flat spacetimes, obviously they have BMS symmetry. So people have defined displacement memory or velocity memory or spin memory. But cosmologically spacetimes, they don't have BMS, or they have BMS like symmetry, so they don't have memory effect. So I got confused in this point.
Yeah, good. So cosmological spacetimes have BMS like symmetry, so not exactly the same as BMS, right? So which had to do with that subtle thing that the conformal weight of the super translations is not just 1, but it's 1 plus s. So it has a similar structure, but it's not exactly the same. I haven't said anything yet about the memory effect, because in order to say something about the memory effect, I need to understand gravitational radiation better. And we haven't quite gotten to that point yet. But so I am going to be cautious and not say anything, but I invite you to work on it and tell me if there is a nice connection, as in the asymptotically flat case, between BMS super translations and the memory effect, the standard gravitational memory effect.
Okay, thank you.
But yeah, we don't know yet.
Okay, so Roberto, he has a mic, you can ask.
In asymptotically flat spacetimes, right, the Bondi shear encodes the two propagating degrees of freedom, and basically in the Bondi-Sachs formalism, it is unconstrained, right?
Correct.
We don't know. In your case, I don't know from the fall-off condition of T mu nu if from the Einstein's equation you can see that the Bondi shear is constrained.
Good.
Or not.
Yeah, we don't see that the Bondi news is constrained if we expand it, but if we try to sort of do the same thing as using these Bondi-Sachs coordinates, we find some, well, to me, still surprising things that I haven't quite understood yet. Yeah. But for instance, so in the asymptotically flat case, the Bondi shear is completely unconstrained, and your mass and angular momentum aspect, they are, well, unconstrained, or they're constrained, but only you still need to give their value at one particular instant, right? So sort of the initial data, if you want for them. It seems that, in this case, the mass is completely determined, right? It's not, that I get an equation for m dot, but I get an equation for m. So things are definitely different, and and since the equations are much more complicated and have many more terms, I'm a bit hesitant. But it seems to me indeed that we definitely still have 2 tensor degrees of freedom. So that's not changing. Luckily.
Yes, my point is that the key aspect here is the fall-off condition of T mu nu, because that determines also the asymptotic symmetry.
That's true.
And then all the physics, basically.
Yeah. As you can see, right, the T mu nu essentially determines the value of S, and that is everywhere in this framework. Yeah, no, it's true.